Okay, let's do 13. Suppose this is a parallel plate capacitor. It is filled up with a dielectric of variable dielectric constant. Okay, so suppose at a distance x, let me consider a strip capacitor. Okay, call it dx. Okay, so here the dielectric constant is given as alpha x plus beta in this layer of the strip capacitor. Okay, so it is given that at x equal to 0 k equals k1, and at x equals t k equals k2. So with this relation we can get the values of alpha and beta. Say when k1, using this one we get k1 equals beta, and using this one we get k2 equals alpha d plus beta, that is k2. So alpha equals k2 minus k1 by d. So this is d. Okay, now what is the capacitance of this strip capacitor? dc equals epsilon naught a k epsilon naught a by dx. Now if I consider this type of strip capacitors throughout the dielectric, then to get the whole capacitance we must get the equivalent capacitance of all these strip capacitors. Now these strip capacitors are in series. Okay, we already have discussed this many times. The charges will be the same on all strip capacitors, so they are in series. So actually for series the equivalent capacitance become reciprocal of the equivalent capacitance is the sum of reciprocal of individual capacitances. So integral 1 by dc will be 1 by c. So 1 by c will be integral dx by k epsilon naught a. Now it's very easy. K is, we know, alpha x plus beta, so put it here, 1 by epsilon naught a dx by alpha x plus beta is from 0 to t. So we get 1 by c as 1 by epsilon naught a, and this would become 1 by alpha log alpha x plus beta from 0 to t. So this would become, so alpha is k2 minus k1 by d, so this will be d by k2 minus k1. This is k1. Okay, and log alpha d plus beta by, it is x equals of beta. Now what is alpha d plus beta? It is k2, right? This is k2. You can do it like this, k2 minus k1 by d into t plus k1 by, it is k1. So D and D gone, so minus K1 plus K1 gone, so it is K2 and this is K1. So D by epsilon naught A K2 minus K1 log K2 by K1. So it will be, C will be epsilon naught A K2 minus K1 by D log K2 by K1. Okay, so this will be the capacitance. So number 14, work done to increase plate separation when battery is connected and when battery is disconnected. So it will be number 14, say the initial plate separation is D1, now it is being increased up to D2. So when battery is connected, then work done will be, it's better to write it as half CV square. Okay, actually change in the potential energy, right? So it will be half C V square. So half V will always be the same, so half C final V square minus half C initial V square. So it will be half V square common, C final minus C initial, so it will be epsilon naught A by D. So finally it is say D2 and initially it is D1, so it would become half epsilon naught A V square one by D2 minus 1 by D1. Okay. It may be negative. Okay, if it is negative, then you will say that it is the work done by the force, and when it is positive, then it is work done against the force, that is work done by external agent. Okay. Okay, so it is when battery is connected and when battery is disconnected. When battery is connected, then we know battery connected means V constant, and battery disconnected means Q constant. So in this second problem we should write it as the same thing, delta U, but this time we should write it as Q square by 2C, that formula. So Q square by 2Ci. Okay, so here it will become Q square by 2 is constant. Now 1 by Cf will be D2 by epsilon naught A, and second term it will be D1 by epsilon naught A. Okay, so it is very easy. 2 epsilon naught A, it is D2 minus D1. Okay, so see, in the second case the work done is positive, in the first case it is negative. Okay, so when V constant, if we increase the plate separation, so actually the capacitance decreases, that means energy decreases. Okay, fine. So it is the work done by the force basically. Okay, and when battery is disconnected, then here the work done is positive. so work done is against the force. So number 15, here this is 2R, this is 16Q, and here it is R, and this is Q. One thing is not given in the problem, that this distance is 10R. Okay, so first you are actually throwing minus Q. Okay, so suppose this is the neutral point where E is 0. Okay, so if this charge reaches at least at this point, then these two forces will cancel. Okay, so the net force on this point on the charge will be 0, at this point on the charge will be 0, and if it just reaches, just overcomes this point, this charge minus Q, then the attraction of this charge will be greater than this one, so it will easily reach this sphere. Okay, so our agenda is to throw this minus Q charge up to this point, up to the neutral point. Once it overcome this point, then it will automatically be attracted towards the smaller sphere. Okay, so first calculate the point, the neutral point, that is E is 0. Okay, so it is 16Q by R square, that is the distance. Okay, call it X, so X square, and this is Q by 10R minus X square. Okay, so it will be, okay, I'm not writing K because on both sides K will be cancelled for 1 by 4 pi epsilon naught. So 10R minus X by X will be 1 by 4. So 40R minus 4X is X. So 5X is 40R, so X is 8R. Okay, so if X is 8R, then the rest is 2R. Okay, distance. So now we have just to conserve the mechanical energy, conserving mechanical energy. See what we will get. If we conserve the mechanical energy, what we will get? At this point the velocity is v0, so half m v0 square, the kinetic energy, plus the potential energy. The potential energy will be, this will be minus, right? So minus K Q into 16Q by 2R, and minus K Q into Q, and this distance, if it is 2R, then this distance is 8R. Okay, fine, this is 8R, from here to here this is 8R. Okay, this much is 2R, total is 10R. Okay, so it will be 8R. Okay, so it is 8R. equals, when it reaches this point, it just reaches this point, so we can say that at this point the velocity is 0, that is, it is at rest instantaneously. So at the neutral point the mechanical energy is kinetic energy is 0, but potential energy will be, now this distance is 2r I have found, so, and this is 8r, so it will be minus kq 16q by 8r minus kqq by 2r. So half mv0 square is k q 16q, take it common by r also, so half minus 1 by 8, and this one will be minus kqq by r, half minus 1 by 8, so it will be, square will be kqq by r is common, so it will be 4 minus 8, that is 4 minus 1, 3 by 8, right? 8, 4 minus 1, 3 by 8. So let's take 3 by 8 common also. So here it is 16 and here it is minus 1. Okay, so it is 15. So half mv0 square is 3 by 8 k q by r into 15. So if I put this one as 4, so then I'll get v0 square as root over 45 by 4 kqq by mr, isn't it? So it will be 3 by 2, v0 is like this, 3 by 2, so 9, so it will be 5 kqq by m. Okay, so if I put 1 by 4 pi epsilon naught, so it will make no difference. 3 by 2, 5 qq by 4 pi epsilon naught m. It will be like this. Let's do problem number 19. In identical capacitors are in parallel, being charged by a battery of EMF V. So charge in each capacitor is CV, that's for sure. Okay, now they are connected in series. Okay, so when connected in parallel, so it is charge on each capacitor. Initially when in parallel, and when in series. the equivalent capacitors will be series 1 by C is like this. Okay, like this. So it will be N by C. So C equivalent will become C by N. So the total charge Q total charge will be C equivalent into V. Okay, so it will be see the total charge is the total charge remains unaltered. That means the total charge of n capacitors. Okay, each capacitor has a charge of CV. So n capacitors has a charge of nq initially, and also when in series this charge remaining unaltered, that is it will be nq. Okay, so it is C by N into V. So it is N CV is C by N into this time the potential difference across the combination is V1, say. Okay, so C and C cancel, so V1 becoming N square V. Okay, it will be N square V. Clear? Okay, Q total is NQ is NC. Okay. So initially it was like this. Is V, there are N capacitors identical C, and like this C. Okay, N capacitors. Then after being charged, they all have the same charge Q. Okay, so after being charged, they are now opened and connected in series like this. So the potential difference they asked across the series combination. Okay, and the condition was when connected in series the total charge of the combination remain unaltered. So the total charge here NQ, here also the total charge will be the same. Okay, NQ. Okay, this is the condition. So the potential difference will be this. Okay, so what will be 18 Q1 minus 2Q, two charges are there, the equipotential surface corresponding to the zero potential. Suppose I have a point here. Okay, let this point be say xy. So this is y, this is our 0 0. So this is 6. So if this is x, so this is 6 minus x. Okay, so what is this distance? Root over x square plus y square. And what is this distance? Root over y square plus 6 minus x square. Okay, so the total potential at this point is 0. So q by kq by root over x square plus y square minus 2kq by root over y square plus 6 minus x square is 0. So it will be simply kq gone. So root over y square plus 6 minus x square is 2 root over x square plus y square. So we get y square plus 6 minus x square is equals 4 x square plus 4y square. Part of x plus x square 4y square. So it is 3y square plus 3x square plus 12x minus 36 is 0. So it is y square plus x square plus 4x minus 9 is 0, isn't it? So if I write yes, y square x plus x square plus 4x plus 4, then I'll get minus 13. No, it is 12, no? Sorry, it is 12. So it is minus 16. So it is y square plus x plus 2 whole square is 16. So see, this is x plus 2 whole square plus y square is 4 square. Okay, so I can write it as this. It's better to write it as this: x minus 2 whole square plus y minus 0 whole square is 4 square. Okay, so it is this locus is a circle, right? Okay, so the locus of xy point is a circle. So the equipotential surface in the xy plane corresponding to 0 potential will be a circle, okay, with center at minus 2, 0 and radius of 4 centimeters. Okay.